Hey, okay, so we want to have a look at section 4.3 here, guys. We've covered Ohm's law, which is really quite basic stuff, and we want to look at an application of Ohm's law, these ohmic and non-ohmic conductors. So if we start off, we'll just speak to the text. You know, that relationship delta V over I, remember delta V can just be can be written just V. It just means potential difference or voltage. Can be used to find the resistance of the material. There's Ohm's law. Now, that characteristic of resistance actually depends upon a few factors. In our last lesson, we said the resistance of the material depends on what it's made of. That's that resistivity, the length of the conductor, and its cross-sectional area. And that's all well and good, but it also depends upon probably one important factor is the temperature of that resistor. And as a slight aside, when you think about the charges, you know, that's, let's say it's a piece of copper. You've got those delocalized electrons cruising through. As we increase the temperature, they're going to gain kinetic energy. So they're going to be bouncing off each other a lot more. And that's exactly what causes that resistive heating, is when the electrons bounce into each other and also the ions that they've got to move through. And as a result then, in general terms, as the temperature of something increases, so does its resistance. Okay? So when we talk about the resistance of a material, it's not necessarily always constant. And that's one of our key concepts. All right. We'll start with how do we use a graph to find the resistance? So, we use these terms ohmic and non-ohmic to define two different classes of resistors. Ohmic simply means that their resistance doesn't change as you tweak the voltage and the current. So if we did a graph of current versus potential difference, and whenever we talk about a graph, the one you do first, mention first, is the Y, the one you mention second is the X. So current versus potential difference gives us the you can use that to calculate the resistance, but the resistance is the inverse of the gradient. Let's look at this graph here. All right, here's our current versus voltage. All right, there's our current versus voltage. Now, our gradient is our rise over run, and in this case it's I over V, right? But the resistance, just gotta wait for the screen there, we're back again. The resistance is V over I, and you can see pretty well straight away, that they're the inverse of each other. Your gradient, which is M, is I over V, but your resistance is V over I. So if we have your current on your y-axis, your voltage on your x-axis, right, your gradient is the inverse of the resistance, or at least the resistance is the inverse of the gradient. So a lot of the time, you'll see your voltage on the X and current on the Y. Even though the resistance doesn't work out nicely. It's the inverse of the gradient. Why do we think we put current on the Y and voltage on the X? Pause, write down an answer, see what you think. So we did it so that, yeah, obviously on the Y-axis is your dependent variable, on your X-axis is your independent variable. And it's not always going to work that way. Often you'll see voltage on your Y-axis, current on your X-axis. What that means then is that, if we look at this graph here, is that straight off your resistance is your rise over run, which is V over I, so that's just your gradient. So when you come along with these questions, guys, first thing you look for is what's on your Y-axis, what's on your X-axis, and then depending upon how that's set up, your resistance is either the inverse of the gradient or the gradient itself. Now, we talked about these ohmic conductors. Let's look at ones where your resistance does change. They're called non-ohmic conductors. They still obey Ohm's law. All right? All it means is that the gradient changes as your potential difference changes, hence your resistance changes. So let's look at this one, and our current is on the Y-axis, potential difference is on the X-axis. So our resistance is the inverse of the gradient. Remember, M is for gradient. Right? Y is equal to mx plus c. Okay? So if we look at it at 1 volt, our current is 1 over 0.2. Remember, it's the inverse of the gradient. So what have we got? 5 ohms. If we crank up the voltage to 3 volts, our resistance is going to be 3 over 0.4, and that's 1.2 ohms. Is that right? 1.2? No. 7.5. 7.5. Can't even. There you go. 7.5 ohms. So compared to at 1 ohm, where the gradient's quite steep, so the resistance is lower. At 3 volts, the gradient's reduced, so the resistance has increased. Bless you. All right. So two main types of resistors, ohmic and non-ohmic. They still all obey Ohm's law. It's just the non-ohmic ones, the resistance changes. Usually due to heating. Okay? So if we look at, we saw those examples. Right, next thing you need to do is getting cracking with exercise, the key work from exercise or section 5.4, and then of course we've got our exercise set 3.